Okay, so welcome everyone to the live lectures of parallel and concurrent programming. So the next 3 weeks, I'll give the lectures still on Zoom, of course, yeah, because we can't go back, unfortunately, but in real time. So if you have questions or remarks, then you can simply raise your hand in the Zoom. And we have two assistants, Nicola Stucki and Guillaume Martes here, who will monitor your feedback and your questions, and who will raise them so that we can discuss them together. So I think the problem is with all this remote teaching that it's very one-sided. There's a lecturer who speaks and the students who just listen. So let's try to break that up. And if you have anything that you want to come up, please don't hesitate and just tell us, because that way I think we will all have more from we will get all more out of that course. Also, you can simply turn on your video. I think Zoom cameras are big enough, then we can see each other. And then you can also raise physically a hand, and we might see each other that way. Okay, so welcome everyone, and nice to see some of your faces, masked or not masked. Let's launch into this module. So the next 3 weeks, we are going to do concurrent programming. And concurrent programming is, in a sense, the low-level basis on what everything else in this course rests. So you've seen the first 4 weeks parallel programming. So all these parallel execution threads, somebody has to launch them and coordinate them and make sure that essentially everything works and that exceptions are caught and all these things. So that's essentially the low-level substrate, which is essentially done with concurrent programming and with concurrent primitives. So the next 3 weeks, we learn about those. And those primitives, I mean, the course is still in Scala, but they're really not that Scala specific. I think let's say the basic building blocks of concurrent programming are quite similar over many languages, and the ones you see here are specifically those on the JVM, so they are the same for Java and for Scala and for other JVM languages, because they're all based on essentially the JVM primitives that the JVM offers for concurrent programming. And if you look outside the JVM, let's say in a typical Linux kernel, C, C++ programs, then often or usually they're very similar primitives that deal with concurrent programming. Some of the languages might be more restrictive. So for instance, if you look at Erlang, it has the so-called actor model. So the actors send themselves messages. If you look at Go, then it's also message-based programming. And if you look at Rust, there's something called structured concurrency. But the low-level things on which these models, these more restrictive models, build is, again, essentially the thread model, which is very, very general, and which we will learn on the following slides. So to motivate here is a program that is in some ways surprising. So let's have a look at what the program does. The program itself is not very surprising. It's pretty, essentially, it just tries to prove a point. So we have two variables, A and B, and we set them to false. Then we have two variables, X and Y, and they're initially -1. And then we have two threads, this one here and this one here. So a thread is a concurrent computation that proceeds independently of the other threads. So what each of the threads does is it goes to sleep, so it waits at least 1 second, millisecond, at least 1 millisecond it waits. And then the first thread sets A to true, whereas the second thread sets B to true. And the first thread then asks if B is set, then return 0, otherwise return 1. And the same thread does the same, but just for VA here. And then at the end, essentially, there are these joins. We'll find out what that is. They essentially, the main program waits for the two threads, and then it has an assertion which says that it can't be the case that both x and both y are 1. So let's see whether that makes sense. So why would that be? How would we argue with that? Well, we would say, okay, we don't know in what order these two threads operate. So let's say the first thread operates by setting A to true, and then the second thread comes, and then since A is true, it will set X to 0. So then there can't be both 1. Or it might be that the second thread is first and sets B to true, but then the first thread would have to here see that the B is true, and then it would set the Y to 0. So one of the two always seems to be 0, right? Let's see what so the official reasoning here is thread 1 writes true to A and reads B and sees false, writes 1 to 0. Thread 2 writes true to B, reads A and sees true, writes 0 to X. And there's essentially several other possibilities, which essentially all, if we do an exhaustive search of the possible transition space, then we always end up with the fact that at least one of these variables is 0, right? So the conclusion is there's no execution in which x is 1 and y is 1. But when we actually run this program, then most of the times that's right, the assertion will not fail. But every once of a while, and that's the infuriating thing, every once of a while it will fail. The assert will crash the program. Bad. So that shows us essentially one very annoying thing, that these things are non-deterministic. They give you different results in different runs. And they also seem to be unintuitive because, hey, we just have argued that there can't be both 0. So something's wrong with our intuition of concurrent programming. And what this course is about is to rebuild the intuition about concurrency, starting from the basic principles. So this introductory example was just an example to show you, well, things are not as clear as they might seem at first. They're actually quite subtle things going on. And that's why concurrent programming is typically an area for sort of experts or people who see themselves as experts. So one has to essentially get some work up some precise knowledge about these systems then before one can reason intuitively about what these things do. Okay, so the goal of the what the concurrent programming is, and like I said, there are several possibilities. We're looking at one of them, the one on the JVM, but each of them has essentially the same goals. So you must answer two questions. The first is how to express that two executions are concurrent. So the basic things, how do you launch concurrent executions, things that can operate at the same time. And then the second question, fundamental question is, let's say you have now a set of this concurrent of executions, how can they exchange information? And that we call synchronize. So how can they exchange some information in a predictable way so that we can actually reason about what each of the executions finds out about the others. So what we're going to do now is we answer these two questions in the context of the JVM memory model. So how does a concurrent execution get specified? So the way we're going to do it is we're going to postulate a method thread, and that takes as its argument a sequence of statements, a block, and it will execute these statements in parallel with the thread that launched it. So essentially a thread. Some languages call it a fork, so that would have been another name. So thread essentially does a fork that now there are two threads, the one that is given in these braces here. and the main thread that launched it. And those two execute concurrently. So that thread method is a utility function that you find in a library, or you can easily write it yourself. Here's an implementation of that thread method. So we have this thread thing method here, and it creates a new thread. So thread is a class in Java lang, so that's really java.lang thread. But Java lang things are imported automatically in Scala, as we know. So in Java lang, there's a thing called thread. And to define a thread, you have to override its run method. So it has a run method that is not abstract, so you have to define it with some body. That defines a thread with a particular behavior that's given by body. That thread is initially inactive, so you have to start it with an explicit command. So t.start starts the thread. So at that point now, the thread will be a concurrent execution, and the thread method, what it does, so it creates a new thread, it starts it, and it returns it as the result. So that way, here in this simple example that we see here, we didn't care about the result of the thread, but we'll see right away examples where we do. So it's important to have an identifier for the thread that we have created. Okay. So one could ask, well, why do we need threads? If we want concurrency, then ultimately, how do we get concurrency in a computer? And we get it by having multiple CPUs, right? So different CPUs can run different things. So can't we just program with the CPUs directly? So instead of having a thread, we could write something like @CPU1 and then the thing. So we just assign a block of things to a CPU to execute. So the problem with that is first portability. So different processors have different layouts of CPUs. Some might have only a single one, some might have 4 or 6 or 8 or 64. So every processor is different. Not every computer might have a CPU called CPU1. And furthermore, the number of concurrent entities in a program is often much larger than the number of CPUs. So typically what we do is we define a much larger number of threads, the number of CPUs, and then most of these would wait on something or another, so only a few of them would be executable. And if we have more executable threads than CPUs, well, then essentially they get each a time slice. So the CPUs get time sliced between the threads that can run. So that way we can define more threads and we can than CPUs, and we can be independent of the actual computer. So the principle then is a thread expresses opportunities for concurrencies in the program. And to start a thread, so we define what the thread does. So in the JVM, we create this thread object and override the run method that defines what it does. And then we start it, and that's done with the start method that we have seen. Okay, so what then is a thread under the hood? Under the hood, a thread is essentially consists of the registers. So R0, Rn, and also the stack pointer and the instruction pointer. So the next instruction, basically all the registers that you can access as a programmer, as well as the internal ones. The complete state of the CPU. And then it consists of a call stack. So that's essentially the stack with the frames and things like that. And the call stack is selectable in size, but the default size is 2 megabytes. And well, you could go smaller, but if you go smaller, then you risk that you then could be a computation that overflows. So 2 megabytes is sort of chosen as sort of a compromise to say, well, we want to have something which is in practice is big enough for all things, and the fact that, well, You don't want to take too much memory. So that means that 2 megabytes. So if you are on a 32-bit VM, then you're restricted to a couple of thousand threads. So that's sort of your upper limit. On a 64-bit VM, that limit, the address space limit is no longer a serious limit. You could have many more. But in practice, there's still pressure that you can't really go over, let's say, more than tens of thousands of threads, because you get pressure everywhere in the page tables, in the operating system scheduler, and things like that. Things are just not built for more than a couple thousand or maybe a couple 10,000 threads. That's your limit. You might say that's plenty enough, and usually it is. But you could also imagine a scenario where you say you have a server and you assign a thread to each communication with a user, and then your number of threads is the number of concurrent users. And there you say, well, 10,000 concurrent users, that's okay, but that's not super scalable. So that means that as soon as, let's say you're, I don't know, a concert ticket reservation site, and you might, at peak times, you might have more than 10,000 users. So then you will run out of threads. So that means that this limit of threads, a couple thousand per VM, is actually a serious limit in practice. And that's why there are new works. Essentially what we will find out is about in the next week about runnables and executables. And there's also a project on the JVM, which is called Project Loom, which wants to essentially have more lightweight threads that are sort of different from the operating system's threads. They call them virtual threads. And the aim is to have not several thousands, but several hundreds of thousands of threads. So that means that you have to be essentially smaller in the memory footprint and everything. Okay, so that's the under the hood situation. So in the if we look at essentially the architecture of the operating system and the CPU, then that's a good image. So essentially you have your memory here, and you have your CPU cores here, and then the operating system has processes. So processes have their own slices in memory, and they have their own, essentially, they execute concurrently, but they do not share memory. So they have different reserved memories, so they share messages through essentially sockets. So that's a typical thing. So operating system allows them to communicate with TCP/IP or other protocols through sockets. And then what you have is in a single process, you have these threads, which then can execute in parallel in a single process. And if you look at, let's say, a JVM instance, then a JVM instance, it shows up as a single process, but it has many threads. And those threads inside the process, they see the same memory. So they share the memory and see the same memory. That's the principal difference between a process and a thread. So each process can have multiple threads, and it starts with one thread, which is the main thread. So it might always have just the single thread, the single main thread, but we have seen we can create new threads with the thread command or by creating a new thread objects, and then we can execute those threads concurrently. Okay, so what the operating system does is essentially it eventually assigns threads to processes. So if you have these threads, then the question is who gets to run, and that's in the end, that's the operating system that decides that. So typically what it does is it uses time slices. So every thread has a time slice of say 10 milliseconds, and it might choose to essentially stop before that. There are commands that we see that thread can essentially give back control before its time expires. But otherwise, after 10 milliseconds, if there are other threads that can run, the operating system will switch the process to run on this other thread. So that's essentially the scheduler that the operating system uses. And To do that, oh yeah, I was getting slightly ahead of myself. To do that, it uses typically this preemptive multitasking. That's the thing with the time slicing. There's another way to do it, which is called cooperative multitasking. So that means that when a thread runs, it runs as long as it intends to, and it must explicitly give control back. Typically, that's called a yield. So a yield says, well, I'm done running for now. I tell the operating system that it can now run some other threads. So that's, in a sense, more lightweight. The advantage is that essentially a thread can choose the points where it's ready to yield, so it cannot be interrupted at essentially arbitrary times where maybe the thread is in a state that is dangerous at this point. So it's essentially it's somewhat simpler, but the problem with cooperative is it's not really um, it's not really it's easy to misuse it. So essentially, it's not robust against misuse. Where misuse means that one thread just runs forever, essentially hogs the resources, could go into an infinite loop or things like that, and then whoosh, that would mean that essentially nobody else gets to run. So preemptive multitasking is mostly what it is these days. It seems that every new language is sort of trying with cooperative multitasking. Um, if I remember, the first threads on Java were cooperative. I think the first threads on Go were cooperative. So were the first threads on Rust. And after a while, they all switched to preemptive because they essentially this problem of hogging CPU resources and not yielding is just too serious, and nobody has found a good way around that yet. Okay, so let's look at an example program after talking so much with threads. So here we have a super simple program. So we have a method log. So log prints the current thread ID. So the thread object, or for Java, that would be a static method, but in Scala we model it as a method current thread in the thread object. So that gives you an identifier of the current thread, just as thread 0 or thread 1 or something like that. And log gives you essentially what thread essentially started the log and the message. So when you write log creating a new thread, and then you define a thread here, and the thread says new thread still running, and then we sleep for a second, so sleep 1000, and then we write completed. So what we will see is essentially the main thread will say creating a new thread, and then we will see the subthread, which will have a number, thread 1 or something like that, will say new thread still running, and then we will see completed. So that's what we would expect here. Okay, so the sleep statement pauses the thread and revives after the specified period in milliseconds. So that means the thread basically will be inactive for at least 1 second. You can't specify exactly 1 second because that's up to the operating system. So the operating system will essentially, after 1 second, just essentially turn the thread on to be runnable again. But then basically it's whenever there's a CPU that can run this thread, and essentially the operating system decides to schedule that thread. Okay, so that program is still deterministic. So we'll always see essentially first this one, then this one, and then this one. That's the order in which we will expect to see the messages. But that's essentially rather the exception. So most programs that we run concurrently are actually not deterministic. So here's a program that is not deterministic. So let's see what it does. So we create a thread and we say new thread running, and we essentially write in the main thread twice triple dots. So here, if we run that, since the program is very simple, we might, you can try it out, and you'll probably see what I saw is basically also this here, 1, 2, 3. But that's actually not assured. So we might very well see, let's say, this one first, and then this one, or that one, or we might see this one first, and then that one, and then that one. That's all possible orders. Because what we have is essentially two concurrent executions, and they progress each at their own pace. So we don't have any control about how fast things go. So for instance, what could happen is as we create this thread here and start it, it could be that that thread gets immediately queued, and then essentially the main thread gets to run and it prints its two log messages, and then we can come back to the thread and run that thread. Or it gets queued, the main thread runs the first log, and then it gets suspended and we do the T thread instead. So then we would have this scenario where we run this first, then this one second, then this one third. Okay, so that was how we launch threads, and so far it was very simple. We have these concurrent executions, we put them in thread, and we launch them, and that's it. The second requirement is synchronization. So that means how do these threads coordinate? That means how can they essentially wait for each other, and coordination is done through communication. So more generally than coordination, it's really how do these threads communicate? And on the JVM, the answer is they communicate through shared memory. So that means one thread can set a variable that another thread can read. So what we'll see is that this communication through shared memory, which is essentially the most general, because it just essentially that's just what the computer is. It's a bunch of threads and a bunch of memory which is shared, right? So we don't really have to build any other abstractions. So it's the most general, and because it's the most general, it can also be the most efficient one. It's basically from which everything else is built, if we have essentially more restrictive abstraction. But it's very general and also quite dangerous. Because what we will see in the next slides on this lecture is we can have so-called race conditions, we can have deadlocks, we can have data races. So we'll get to know what that is and how to essentially tame the complexity that this very general communication model throws into our way. Okay, so before we do the more advanced things, here's the sort of the super simplest one, and that's just that we want to wait for a thread to terminate, because we said, well, hey, we have two threads, so they fork, so that's essentially the thread 1 now, or T, and here that's the main thread. So will there be forever concurrent, or is it possible that essentially the main thread will essentially continue and that thread will terminate? Threads terminate, of course, because I mean, if we have this thing here, if this thread has printed, then it's done, so it can terminate. But the question is, can the main thread actually observe that? Can the main thread say, I wait until this my thread is terminated? And the answer is yes, it can. That's done with this join statement here. So the main thread here, and now here do the low-level thing. So these first things that they are equivalent to just starting a thread with the thread method. So we start the thread, we build the thread, we define the thread, we start it, and then we join it, which means we wait until it's finished. And then we can say, then there's a final printer which says that the thread is finished or joined. So the call t.join lets the calling thread wait until thread t is terminated. So that's essentially the simpler thread start that we have seen here. We create a thread, we join it, and then we print the final statement here. Or as a diagram, see that here. So here we have, so typically in these diagrams, we represent traits as vertical lines. If they're concurrent, then there are several ones. And causality as arrows. So here we have these two threads, and as long as things are on separate lines, there's no order between things. So they can execute at any speed. But if we have an arrow here, like this one here, then that means that essentially what happens here will happen after the things that happen in the main thread. So our sequence of actions is now we create this thread, we start it, that causes a new thread to start, and that proceeds independently. At some point, that will do the print on, and at some point, the main thread will do the join. And what happens for the join then is that at that point, the main thread will suspend. So you see that with the dotted line here. So it means it will not go to the next statement. It won't do anything until it's notified that the second thread, the T thread, has terminated. And then it will go on and do the final printing. So that's essentially the diagram that tells you how these two threads operated here. And we will see, we'll see further diagrams in the next slides. Oops, sorry. Okay, so one guarantee that might be trivial, but we'll find out later that it's actually not. It's worth spelling it out. Is that when a join returns, then the effects of the terminated thread are visible to the thread that called the join. So the question here is when we print assert A, what is A? So the main thread set A initially to false, but the concurrent thread set it then to true. And essentially, by virtue of this join that we have waited for the thread, there's an implicit guarantee that if that thread is finished, then actually the variable will also have flipped for the main thread. It will see the flipped value of the variable that the T thread changed there. And we will actually find out that that's an assurance, that's a guarantee that's far from obvious. It's obvious for a programmer, but it turns out that very similar guarantees, like the ones initially where we said in this initial puzzling example, can they both be one? That there's a violation of those things where we think that things happen in a certain order, but it actually turns out that certain things have not been communicated to certain threads. So that will be a problem that we will have to deal with towards the end of this lecture. Okay. So that's good. So we know that now the effects of the terminated thread, at least they're visible to the thread that called join. But on the other hand, that's not really enough. A join is not useful enough because it always demands that the target thread terminates. So we will also need to see the effects of another thread while they're still executing. And what guarantees do we have then? So not just after they're done, but while they're executing, what can we see from what does a thread does? Okay, so here's a example that shows that the sort of the dangers of concurrent computation, or the first danger, and that's essentially interleaving. So consider the problem of implementing a UID generator for unique IDs. So here's what we would typically write. So we would have a UID count, and we say, well, to get a unique ID, we just return the current value of count, and I bump count by this one. So count just gets, each time I call it, I just increase the counter, and that way everybody gets a fresh ID. So UID is initially 0, so get unique UID. What does it do? It says my fresh UID is current count plus 1. Then I update the count to be fresh UID, and I return fresh UID. In a sequential setting with a single thread, that's completely bulletproof. It's clear every call to get unique ID will yield a unique number, monotonically increasing numbers. That much is certain. But the question is, does that hold also if there are several threads in a concurrent setting? If there are several threads that all call get unique ID, can we be sure that each call gives a thread a unique number? So we can put that to the test. We can write a little program, call it threads get UID. That's my main method. And what it does is it creates a thread, and each, the main thread and the fork thread, both print 5 unique IDs. So here's my method, print unique IDs. It gets told how many IDs should be printed, and it just essentially goes with a for loop for 0 until n. It does a get unique ID, and it then prints what unique IDs were generated. Okay, very simple. And then at the end, we join T and we're done. So it's a bit difficult for me to switch to a live terminal here because I'm working on the iPad. And so what I did is I ran this, and here's essentially the output I got from 5 runs on threads get UID. But I encourage you to actually try these things out yourself. So we publish the slides and play with these things. So don't take my word for it. So what happens here is that in the first run, we got unique IDs. The first vector got 1, 3, that's one here. Second one got 2, 5, 7, 9, 10. So that's fine. Everybody got a unique one. In the second run, they got different UIDs. So the first vector got 1 to 5, and the other ones got 6 to 10. That's also fine. They're all different. That repeated itself 3 times. And then in the 5th run, something interesting happened. The first vector got 1, 2, 4, 6, 8, and the second one got 1, 3, 5, 7, 9. So they both got 1. So obviously that's not unique ID. So they both got 1. And that's sort of just the typical thing that we see. Here we were sort of slightly lucky that 1 out of 5 we got a bad behavior. It could be 1 out of 5,000 or 1 out of 50,000. And that's what makes concurrent programming so difficult, that the error cases are not predictable at all. So they can be essentially depend on very essentially small variations in the execution speeds of these threads that might not essentially manifest themselves on each run. So let's see what happened here. So why did it go wrong? How can we explain that? Anybody has a theory how we can explain that? Here was our critical program. So why would the concurrent execution go wrong here? Let's go. So let's do it with our thread diagram. So here we have the actions that each of these threads does when it calls getUID. And here's the sequence where it goes wrong, the possible sequence. So in that sequence, the first thread would compute its fresh UID from the initial value, which is 0. So 0 plus 1. Before it goes on, the second thread would do the same thing. It would also take a 0 plus 1. Then both threads essentially compute UID count to be 1, update the counter to be 1, and return the count. So that way, both of these threads gets 1. Okay. So what happened then was that in this getUID, here we go, each of these executed this statement here, and in the same state, and then went on to essentially do the rest. Could we have done things better if we had written immediately fresh UID plus equals 1, let's say? And the answer is no. It would be the same thing, because that looks like a single statement, but it isn't. It will essentially decompose into this and that. Oh, sorry, that would be UID count, UID count. So if you write UID count plus equals 1, then the compiler will essentially reduce it, expand it to those two statements here with a fresh variable or register value. And that has, of course, exactly the same problem. So the problem is that these individual instructions, which are, in this case, different expressions, different statements, but could be just machine instructions on the same statement, they can be arbitrarily interleaved by these two threads. Okay. So that scenario is called a race condition. A race condition occurs when the behavior of the system depends on the interleaving of executions. So that means that the outcome of the system depends on the precise timings on when threads are run and when they are paused, and maybe the CPU switches to a new thread. And of course, these things are unpredictable. They will change from run to run or from machine to machine. So another beautiful thing is that things might look completely bulletproof on your machine, but then you ship the program to the client who has a different operating system or different CPU configuration, and suddenly things start failing intermittently. So that's also possible. Okay, and so those are races. Race conditions are then essentially things that depend on the precise timing, on the interleaving of these executions. Okay, so what can we do about that? So what we would like to ensure is that all operations of getUniqueID are performed what we call atomically. So undivisibly. So atomically means that either none of them is executed or they're all executed one after the other without any other instructions being inserted or that can observe a partial result or things like that. Without another thread, so without another thread, reading or writing intermediate results. And the way we do that is that we ensure atomicity by wrapping code in a synchronized. So synchronized is a special call on the JVM that says run the body of that we pass here as an atomic sequence of operations. Okay, so with synchronized, what we have is essentially we force the possible executions. So you see here, with synchronized, we say these three instructions have to essentially appear one after the other. There cannot be any interleaving with another thread. So with synchronized, we would have this situation where the first thread essentially does the getUID, and the second thread, it would can of course concurrently try to do the same synchronized, but it would be blocked. While the first thread executes the synchronized, it would be blocked. Execute what synchronized? So that's a fine-grained thing. So essentially what it says, any operation in this getUID object. So synchronized is always run specifically to an object. So this thing would be essentially this dot synchronized. So it's the current object. And it says no two synchronized operations can run at the same time on the same object. So that means that the variables of that object, in this case, the UID count, they are protected. They can be essentially accessed at the same time only by one thread. And that thread will essentially run the synchronized to completion before any other thread can do something like that. Okay. So in Scala, synchronized is treated as a member method of anyref for object, and Java does pretty much the same thing. It calls anyref object. So synchronized is essentially available as a method on every object there is on the JVM. And in the call object.synchronized and then some block, the object essentially serves as a lock. So that means to execute block, the thread that wants to execute it has to hold the lock, the object lock, and at most one thread can hold the lock at any one time. And once block is finished, the thread will release the locking again. So consequently, if another thread is already running synchronized on the same object, that means holding the lock, then a thread calling synchronized gets temporarily blocked until the lock is again released. So that's how it's done on the JVM for essentially ensuring atomic operations by locking. Okay, so I said on the JVM, synchronized is a method of object. So that means it can be defined on any object. And that actually imposes a significant runtime cost. That costs you up to 1 word in the header of each object, just essentially to keep the synchronized state and things like that. So that's generally considered to be a design mistake of Java. To say, well, no, not every object needs to be essentially have this locking operation defined. So typically, what we want rather than what Java provides is to do synchronized only on instances of a special class. Let's call it monitor. We'll see later on what a monitor is. It's a thing that has synchronized and some other methods like wait and notify that we'll get to know as well. So we would have there certain locking objects, call them monitors, and they can have synchronized. And that's what all the examples in this course do. So in this course, the monitor is really, you could say it's superfluous because, well, you could lock on any object, not just on monitor objects. On the other hand, if you run your projects, your homework examples and your tests, then it's very important to do synchronized only on monitors because our testing framework requires to extend from monitor, because what it does is that it has an override of synchronized in the monitor class, which is provided by the testing framework, which essentially does what the testing framework does essentially is to give you a bit more randomization when threads are run, because the JVM is, like I said, it depends on the timing and often it behaves the same way all the time. So to find errors, it's better to essentially have more variations of possible interleavings, and that those are forced by the testing framework. And to do that, it has to override synchronized. So that means it's good practice to say synchronized will only be executed on instances of monitor. Okay, so let's do a slightly larger example. We've seen in the functional programming course several examples of bank accounts, so let's keep to that. So what we want is to express money transfers between bank accounts. So what we'll see what that needs is that we have several synchronized statements that can be nested inside of each other. So what we want to do now is an online banking system in which we want to log money transfers. So first, here's the code to collect log messages. So we would have, let's say, transfers. It's an array buffer of string. So that's essentially something we put every log message into. Then we would have essentially a lock, which is called here log. And then we have the log transfer, which essentially says, well, I transfer a given sum of money, n units, to somebody with name. So what that would do is it would add that message to transfers. And it needs to be synchronized. So that's important because plus equals is not by itself atomic. So plus equals contains, of course, many instructions, and there's no protection around it. So if two threads execute plus equals at the same time, then what could very well happen is that the system gets essentially crashes or gets into a bad state because it's not built for that. Plus equals is built to be used only by one thread at a time. You might say, well, isn't that a problem with plus equals? Shouldn't every operation be thread safe, that it can be used from several operations at a time? The answer is that would be quite expensive. So essentially all these protection operations that essentially have to ensure atomicity with multiple threads, they cost quite a lot of cycles. So in the interest of speed, typically things don't do that. And you have essentially you have to pick your own synchronized blocks to make sure that different threads don't use the same operation in the standard library. So a good example was in very early on with Java. Java had a string buffer class, still has it. Java never gets rid of anything. And that is synchronized, and also hash table. They both were synchronized automatically, couldn't be misused. All operations were thread safe with multiple threads. And then sometime later, Java decided that these operations were really too slow. In benchmarks, they were just so much slower than the alternatives. So there are now new operation called string builder and hash map. And the essential difference is that the new ones are not synchronized. So they rely on you to essentially ensure that one thread only accesses these things at the same time. And for that, the new ones are faster than the old ones. So that's typically the trade-off that you have here. But since basically a lot of concurrent programming is done for speed, essentially we want to make use of all these CPUs that we have to make your program faster. So to get speed, you don't want to essentially start by slowing down things by having overly conservative interfaces that essentially are then slower than a single-threaded thing. That's a bad way to gain speed. So that's why essentially these things are typically optimized for maximum potential speed and efficiency, and they are pessimized for safety. So the safety is what you have to provide when you program these things. Okay, so that was the logging. So now the accounts. So here's my bank account example again. So we have now a name to a bank account. It's no longer anonymous, and an initial balance, and a variable that keeps track of the current balance. And then we have essentially here two operations, balance and add. And balance just returns the current balance, and add adds to the current balance, and both of them work in a synchronized. So why do they have to work in a synchronized? Well, for the add thing, it's clearer. You see here there's this operation that we saw with getUID is tricky because it's really multiple operations. It's a read followed by an add followed by a write, and of course if you get the unique IDs wrong, if this is not in a synchronized, then here analogously you would get the bank account balance wrong, and that's at least as bad as getting your unique IDs wrong. So you have to put these things in a synchronized. Okay, and then we say for transfers of more than 10, we do a log. And then we also have a getUID. We'll need that later. Okay, cool. So let's go on. So here's now some test code that simulates bank account movements. So we have two account holders, Jane and John, and then we have 3 threads that do transfers. So here we have 1, 2, 3 transfers, and then we essentially just log what they are. So we have 2 nested synchronized calls. We have one on add here, and we have one on log. Okay, good. So that was essentially a account example where just somebody anonymous adds or subtracts something from an account. Let's take this one step further and do a transfer between 2 accounts. So now we want to have a single operation that says I want to transfer from A to B n amounts of currency. So what we want to do is we want to lock both of these accounts before we add n to one account and subtract n from the other account. Why do we want to lock both of them? Well, because otherwise the system could be in a state that is not in equilibrium, that is illegal. So let's say we don't have things, or we do each of these operations separately. Then here we would have a state where A has some money that B hasn't essentially relinquished yet. So we would create money out of nothing. And if we swap them, then of course it would be the other way. We would reduce from B before we add to A. And if we somehow could get into observe the system state between that, we would essentially get an inconsistent result. You could say, isn't that academic? Does that actually happen in practice? And the answer is yes, it happens. There was a big bug in Ethereum, the smart contracts cryptocurrency thing, where somebody essentially exploited precisely this thing, that the locking wasn't correctly done on a transfer. So essentially what these things did was to essentially, they, with a clever call them again, they could engineer a system where you could create a lot of Bitcoins or Ethereum coins, I don't know what they call it, out of nothing, and get a lot of cryptocurrency which didn't really exist. So this was so bad that I think it was more than 1/3 of the value of the whole Ethereum network. And I think they did a hard fork, but I'm not exactly sure what happened afterwards with that. So yes, I mean, these things happen in practice, and they're very embarrassing when they do happen. Okay, good. So we have done this, so we feel good, right? But let's put it to the test. So we test it here. So let's say we have these two accounts as before, Jane and John. And then we do some transfers, just a single coin from Jane to John and from John to Jane. And then we're done, and we just print the balance. That should work now, right? So what behavior do you expect to see here? The first behavior would be that the program terminates, and both accounts have the same balance at the end as at the beginning. So nothing of this Ethereum thing where one of them gets filthy rich. The second possibility would be it terminates, but the accounts have a different balance, so that would be a bug. The third one would be the program crashes, and the fourth one would be the program hangs. What do you expect to see? Maybe just a show of hands, who expects good behavior terminates with accounts having the same balance? Let's see. Unfortunately, I can't see it. Okay, okay. Okay, so who thinks? Okay, well, I go right to the thing. I give you the solution. So it could happen that the program hangs. So how could that happen? Okay, so for that we have to look back at the actual program here at the synchronized. Okay, no, sorry, that was it. Okay, so what could happen is that we have John and Jane. So let's say John wants to do a transfer to Jane. So it says John.synchronized. And then it wants to say Jane.synchronized. So that's essentially John's timeline here. And then it wants to say essentially add n and add -n. Okay, so let's look at Jane's timeline now. So if Jane goes at the same time, then essentially it would do a transfer from Jane to John. So there would be a Jane.sync here. Okay, so both of them succeed. So now essentially we are blocking. And now John wants to do Jane.sync. So it can't do that because that lock, the Jane lock, is already taken. Jane took it. Okay, now it's coming back. Okay, apologize for that. Good, so where we were was essentially John has grabbed the John lock. Jane has grabbed the Jane lock, and now each of them wants to grab the other lock, and of course, so nobody will make progress. So essentially, John can't grab the Jane lock because that's already taken, and likewise, Jane can't grab the John lock. Okay. So this situation where no thread can make progress because each thread waits on some lock is called a deadlock. And what typically happens in the JVM is that when there's a deadlock, then threads don't make any more progress. So you typically observe that by essentially nothing happening. So you wait and there's no further output. You don't see anything. What you can do then is you can essentially have a tool like Visual VM, or you can do essentially a control or command backslash. That if you type that into the terminal that runs the JVM, then it will give you a so-called thread dump. It will tell you essentially what threads it has and where they are. So then essentially you look among all the threads to the threads that do the computation. So typically they're easy to find because they have stack traces that you recognize. That is essentially your program, and you see where they're stuck. And that's a good way to essentially diagnose a deadlock. So even though deadlock seems to be kind of a lot scarier than a race condition, deadlock is already a very scary name. It's actually easier to debug. So you typically see when it happens, you just look at the stack traces and you see where it is. Whereas a race condition is much harder because it's some behavior that does something in unpredictable ways every full moon or so. So it's much harder to actually trace down what that is. But nevertheless, of course, a deadlock is a real problem. Your program essentially will just stop working, and as such, we need to avoid it. So how can we avoid it for this program? So the idea is that what we need to avoid is that two threads grab the locks in essentially different orders. So John grabs first John and then Jane, and Jane grabs first Jane and then John. And that means that both of them could end up with half of them and not make progress. So if they would essentially make them agree that they each grab the locks in the same order, so let's say first Jane, then John, then we wouldn't have a problem. And that's essentially what the solution does. So the solution here, what it does is when we do the transfer, it actually looks at this get UID thing that I've defined, get the unique ID. So now we have a total ordering between threads, and we say we pick the one whose UID is smaller, and we first grab the lock of that thread and then of the other, and then we do the adjust. So that way, essentially, both John and Jane will grab the two locks in the same order, and that way we won't have a problem because essentially somebody gets to grab the first lock, the A lock, and that process then will find the B lock always free. So it can essentially do their thing, terminate, release the locks, and then the other can grab them. Okay. Good. I think now is actually a good point to break because we had already an unwanted 5-minute breaks. Let's maybe make a pause of 10 minutes and meet again at 34 for the rest of the lecture. If there are questions, please raise your hands. I stay around to answer them.
Okay, hello, can you hear me?
Okay.
Yes, great. So just to make sure I understood it correctly, suppose we have a computer with 8 CPUs.
Leo, can you speak? Are you unmuted?
Muted. Can you hear me?
I can hear you.
Yeah, we can.
Sorry, it was my control. Can you please repeat the question?
So just to make sure I got it correctly, if we have a computer with 8 CPUs, yeah, 8 cores,
yeah,
and we run a program that, let's say, generates a lot of threads, like each thread generates two threads and so on.
Yeah.
This program will at most run 8 times faster than if we run it sequentially.
That's correct. Yeah.
Thank you.
Yeah. So you can only get the maximum amount is the number of CPUs that you have, or rather, there's a modern CPUs often have so-called hyperthreads, which are typically twice the number of CPUs. So Intel CPUs have, let's say, 6 CPUs and 12 hyperthreads. So then essentially the number of hyperthreads is the theoretical maximum limit. What the hyperthreads do is that if you have, let's say, a main memory operation, which on a modern CPU takes something like 50 cycles or so to get back, then during those 50 cycles, it will not just wait, it will switch to the other thread. So that means that they need to be able to switch very quickly between these hyperthreads. And that way you can get, I mean, if your program is memory heavy, then you can get more execution out of that. But in practice, it doesn't really matter that much. So often it's really the number of CPUs. And that, I should say, is an upper limit. So typically, it actually takes a lot of work to get that. So sometimes you see no speed up. So sometimes you see maybe, typically, if you have 8 CPUs and you see a speed up of let's say, half that, 4 or 5, then that's already pretty good for general purpose code. For numeric code, it's easier. You have essentially, the operations are more predictable, and there you get more. You get often closer to the theoretical limit.
Thanks.
Yes. So I was wondering, suppose you define a method main, function main, that is not, let's say, a part of an object that derives of monitor. Mm-hmm. And let's say I run something like this dot synchronized on a block of statements. Mm-hmm. Does this refer to some global object that derives of a monitor, or is it something that derives of any ref?
So let's see. So what's the prefix of the synchronized? So you run the synchronized on what object?
Well, I suppose this, but I'm not sure what else you would run it on.
Oh, this. Oh, and you say, what if I am in some global function?
Yes.
So the answer is on the JVM. There are no global functions. Everything is in an object. So in Scala, we just pretend that there are global functions. So what really happens is that they will be packaged in an object, which typically has the file name of your program in it, so package $file name or something like that, and that will be the object that runs the monitor.
Okay. Is this similar to like the object type in Java? Like
object is a class, and the synchronized is running on an instance of that class, so a runtime object.
Okay.
So object, there is no global object as a value. It's just a class. It's a template from which you can create objects.
All right, that makes sense to me.
On that. It has to be some object that somebody created at some point.
Thank you.
Welcome. I just have to get back my screen here. Yeah, good. Okay, so before the pause, we saw essentially two of the problematic conditions for concurrent programming. One was race conditions, data races, and the other was deadlocks. So what we look at now is we get some more mechanisms to actually control and coordinate threads to avoid these two problems. And the mechanisms will also be part of monitors. Because monitors, it turns out that beyond just doing synchronized, they also offer specific operations for waiting for a condition, for waiting for specific conditions, for instance, a particular value of some variables. So these also form parts of monitors. In Scala and Java, then the synchronized statement has a dual purpose. It can be both used as a lock, and as we'll see, it's also important for these waiting things that we can wait for conditions. Oops. So to demonstrate that, I want to introduce a commonly used data structure for synchronization, and that's a buffer. So a buffer is essentially a thing there where we have a number of places which act as a queue, and essentially we have a producer that adds things to the queue, and we have a consumer, or several ones of them. So we might have several consumers and several producers that essentially deposit things in the buffer and that take things away out of the buffer. And these buffers typically have a finite sizes, so when they're full, then producers have to wait until they can produce further elements. And when they're empty, consumers have to wait. And to keep things as simple as possible, for the moment, we'll just look at a buffer with a single place. So a single place here, producers put something in the place, think of a mailbox or something like that, and consumers take it away. So we have these producers and we have the consumers, and the one place buffer then has the following invariants. So producers send an element to the buffer, consumers take it. At most one element can be in the buffer at any one time. That's the situation with the one place buffer. For an arbitrary buffer, that's one is replaced by n for some number n. And for the buffer, we say if the buffer is full, then producers have to wait. And if the buffer is empty, consumers have to wait, right? So that's what we want to do. So here's an outline of a one-place buffer. So we say we write a class, one-place buffer. It takes an element type of the things we put in the buffer, and it's a monitor, so it has synchronized blocks. And what we have is essentially two fields. One says full, is the buffer full or not? Initially, that's false. And the other says element, which is essentially defined as the last element that was written to the buffer. So initially, that's uninitialized. Uninitialized is a special thing in Scala 3, which you get from a package called scala.compiletime. Uninitialized basically just says, well, I won't put a variable, I won't put a value in that variable initially, because after all, what value could you put in there? The variable is of type lm, and lm is a type parameter. We don't know what a possible value for lm would be, but we don't need a possible value because, hey, the buffer is empty. So we express that with uninitialized. In current Scala, so Scala 2 and earlier Scala 3 things, that was just expressed as, equals underscore. So the underscore said it's uninitialized, but in the latest iteration of Scala 3, we decided that we want to get rid of all non-essential usages of underscore, and this was one of them where it was sort of mysterious. So that's why we renamed it to uninitialized, and you have to import it from compile time. Good, but that aside, let's look what the buffer actually does. So it has two operations, put, which is called by a producer, and get, which is called by a consumer. What would put have to do? It would have to say, well, if the buffer is full, then we have to wait. And I leave that open for the moment, so what waiting means. And if the buffer is not full, well, then the element can be deposited in the element field, and full can be set to true, and that's it. So get is the dual of put. It says, well, if the buffer is not full, then it has to wait, triple question mark. And otherwise, well, if the buffer is full, then from now on, full will be false, and the element in the buffer will be returned, right? So that's the implementation, except for these two uses of the triple question mark. So we have to fill that in. So let's see what we need, what we can do there. So one way to do it would be to say, well, maybe we should have a loop and just say, okay, the put operation would call try to put, which returns a Boolean, and that could say, well, if full, then I can't put anything in the buffer, so I return false. And otherwise, I do what was done before and return true, that try to put succeeded. And then the actual put operation would be a while loop, which says while try to put failed, do nothing and try again. So that technique is called polling or busy waiting. And it has a problem, and that is it consumes compute time while waiting. So the buffer might stay full, let's say, for a long time. And that means that the thread, that producer thread would essentially go around this loop, this very tight loop, millions of times to just say, well, is it empty yet? Is it empty? Can I put something in there now? Can I put something in there now? And so on. And of course, that's wasted effort and wasted CPU cycles and wasted energy. So we shouldn't do that. So one should do these things, these busy polling and busy waiting, only for conditions that we know will essentially block us only for a very short time, some cycles, let's say, but not definitely not for things that might block us for an indefinitely long time. And in this example, hey, we don't know when there will be a consumer that will actually take out elements from the buffer so that we can put things into it. Okay, so what we need then is more functionality in our monitors, and that's what essentially we will look at now. So we will make use of the following methods here. There's a wait method that suspends the current thread, and then there are two versions of notify and notify all. So ideally, in this model, what we would like to do is we would say, hey, we want to wait for a condition. Let's say wait until the buffer is empty, or that could be an arbitrary complex Boolean condition. But that would be pretty complicated to compile, to implement, because essentially we as a programmer would say, well, you as a compiler, you should know when you need to reevaluate that condition. So what the JVM actually has is something much simpler. It just says, okay, we wait unconditionally until somebody notifies. So we'll see that in action in the next slide. So one note is that all these methods can only be called from inside a synchronized. If you try to call it from outside, you'll get a runtime error. Okay, so now what we have here for the one place buffer is the new implementation, which says for the put, while the buffer is full, wait. So wait would just suspend, and until somebody calls notify. And then the getter, the consumer, would essentially say while not full, wait. So let's say we have an element in the buffer, so the consumer would, it's not full, sorry, the buffer is full, so the while loop would be skipped. And then the consumer would say, as before, full equals false, and then it would have this notify all operation. So notify all is essentially an operation which says, hey, the condition, the crucial condition of this buffer has changed. Now please, any thread that got suspended, wake up and you can try again. And because of this try again aspect, it's also important that this is a while and not an if. So what the producer thread, so what this thing would do is it would wake up all threads. There might be many producer threads that are weighted like that. And then one of them, those threads, so they all would essentially wake up, but they're still in the synchronized. So that's important that wait and notify all are only in the synchronized. So that means only one of the producer thread gets access to the monitor at this point. So the first thread that gets access to the monitor essentially wakes up in the wait, goes around the while loop again, and asks, well, is the buffer still full? And of course, the answer will be no, because there was a consumer that just made it empty. So then it can exit the while and essentially do the filling and notify all. Whereas the other producers then, that essentially all were woken up by the notify all, they would then, after the first thread exited the synchronized, they would then go into the synchronized, but because there's a while in here, they would say, well, is the buffer full? And the answer is yes, it's still full, because the first producer that got into the buffer after the consumer turned it back to full again. So all the other producers would have to wait again. So that while here is important to ensure consistency, because otherwise what would happen is that multiple threads would wake up, one after the other, they're in a synchronized, and then each of them would deposit its element into the element slot and set full true. So that means that elements would get lost. So if there are two producers that do that, only the element of the second producer would be in the element slot, and the element of the first producer would be overwritten. So that would be incorrect behavior that we have to avoid here. Okay, so what we have, what I've explained is why while full do wait instead of if full then wait, right? But there's another question. So why notify all instead of notify? Wouldn't it be easier if one thread, let's say the consumer thread, just wakes up one thread? So the difference between notify and notify all is notify wakes up one of the waiting threads. It's not specified which one, but a reasonable implementation will probably order them by the time they suspend it and wake up the thread that sort of got suspended the longest. So why not write notify here? So the problem was we woke up all these threads, and so now they all rush into if there's several producers to deposit that thing into the same buffer. Why not just wake up one of them? Wouldn't that avoid the problem? And the answer is no, unfortunately not, because this notify, if we wake up just one of them, and we have no guarantee that that thread is not a consumer. So there might be multiple consumers as well as multiple producers waiting for to enter the monitor. How could multiple consumers wait for it to enter the monitor? Well, essentially, there's this synchronized here, so they might just arrive at a time slightly afterwards and want to enter the monitor. So it could be that we have multiple consumers, or that they piled up from an earlier thing where we had essentially, we didn't have enough elements, and now we have 10 consumers waiting, and then one consumer got in and got the first element out after a producer. So then that consumer notifies some other thread. It could well be that that's a consumer. But then, of course, that would be pointless, because then the consumer would essentially immediately go into this thing here and say, well, it has to wait again. The buffer is empty because the first consumer already emptied it. And then again, it would be incorrect. So now essentially we would get a deadlock. We wouldn't make progress because we notified only one thread, and that was the wrong thread. There was a thread that couldn't actually do anything. So that's why in the JVM model of monitors, typically you do notify all, and then each of these threads sort of re-establish their condition with a wait. Okay, so wait, notify, notify all should only be called from within a synchronized on this. And wait will release the locks, so other threads can enter the monitor. And notify, notify all, schedule other threads for execution after the calling thread has released the lock. Yeah, that's also important. So you could say, well, if there is this this notify all here, does that mean that essentially now one of the threads gets essentially woken up and maybe in this thing here, does that mean that there are now two threads in the monitor, the one that got woken up and the one that notified? And the answer is no, that actually doesn't happen. We wait until the notifying thread has safely exited the monitor, and then the system will essentially wake up one of the threads that got notified and let that thread in the monitor. So it's always, we maintain the invariant that at any one point, only a single thread is in the monitor. Okay. And the caveat on the JVM runtime, it's actually possible that threads will spuriously wake up. So that the calling thread sometimes wakes up even if nobody called notify or notify all. It's rare, but it can happen. I'm actually not exactly sure why it can happen, what goes on there in the JVM runtime. But that's actually not a lot of importance, because if we properly protect our locks with whiles like here, then that's okay. So that's why it might get woken up. It's why what the runtime will ensure is that it's the only thread in the monitor. And then the thing that matters is essentially what is the value of this condition. So if the condition is essentially the one that it needs to go on, then it will do that, and otherwise it will just wait again. Okay. Okay, good. So when we discussed fork and synchronized, we didn't actually look at what the visibility of the memory writes was. We just assumed that a memory would just be written as usual. So what we've learned is that the join method ensures that all the writes of the joined threads are visible to the threads that call join. And actually the same happens with the synchronized. So the synchronized statement ensures that all the writes by thread A that precede the release of the lock by that thread A are visible to any thread B that subsequently acquires the lock. We'll see what that means in a second. So these statements, they are part of what's called a memory model. So a memory model is a set of rules that defines how and when the writes to memory by one thread become visible to other threads. So a memory model should be able to clarify essentially situations like this one, the introductory example where we said, well, we have these two threads and they assign A and B and X and Y, and at the end we would like to assert that X and Y are not both one, but it turns out that's not the case always. The memory model does not guarantee that outcome. So let's have a look at memory models that what kind of memory models would make sense. So what we implicitly assumed in this introductory example, and what in the end turned out to be not the case, but it would be very reasonable, is the so-called sequential consistency model. So what that means is that essentially every read and write that a thread does happens in the program order, and every read and write goes to main memory. And the threads would essentially execute instructions in an arbitrary interleaving. So one thread executes one instruction or several, and then the other threads execute some instructions, and then the third thread introduces some instructions, and it's essentially it's all interleaved. So it's as if each instruction, the instructions of a thread were a deck of cards, and to get the total behavior, you essentially just merge the two decks of cards in an arbitrary randomized version, which means that the cards of a single thread are still in the same order, but they're arbitrarily merged with the cards. That means instructions of the other threads. So that's what the sequential consistency model is, and it makes a lot of sense. So formally, what we say is consider all the reads and writes to program variables. If the result of the execution is the same as if the read and write operations were executed in some sequential order, and the operations of each individual processor appear in the program order, then the model is sequentially consistent. So it means all instructions, the total the behavior of the program is like a sequence of instructions where each instruction is taken from one of the instructions of a thread, and they appear in the order they're given in the thread. So, unfortunately, as we saw in the experiment, multi-core processors and compilers do not implement the sequentially consistency model. Some people tried to do it and evaluated how expensive it would be, because it's a nice model to have. And the takeaway was it would probably slow down execution by 20 or 30%, depending on how much it's optimized. So typically people deem that that's too expensive because, like I said, concurrent programming is all about speed. So essentially to get a penalty of 20 or 30% was seen to be unacceptable. So we do not have the sequential concurrency model. So why not? So one reason is CPU registers. So registers hold local copies of memory values, and if we update a register or we write a register to main memory, then typically that goes into a write buffer. So that means it will be flushed to main memory at some point, but that point is in the future. So we don't guarantee it right away. So that means that each core might have a different copy of shared memory in its registers. And as it works on the registers, it gets out of hand. There's not a single copy of that variable anymore. And those registers get written back to memory at unpredictable times. And another problem is optimizing compilers, because optimizing compilers typically reshuffle your instructions, and they typically want to reshuffle your instructions with the assumption that the program they see is run in a single thread, is the program of a single thread, because otherwise they could do much less. They couldn't do many optimizations if the answer was, well, yes, but at between any two instructions that you've written, another thread could observe any variable that you write, then there's much less that an optimizing compiler can do. So that's essentially the two things. One is the memory hierarchy, where things live in registers or L1 caches or things like that, and haven't been essentially flushed to main memory yet. And the other is optimizing compilers. That's the two impediments for sequential consistency. Okay, so what we have in the Java memory model is a weaker version. So what that memory model does, it tries to approximate, it tries to find a set of reasonable guarantees for processors. In reality, each processor has certain guarantees that they provide, and typically they're the same over the processors of a company. So basically, most Intel processors would have one model of consistency that they guarantee, weaker than sequential consistency, but some other models. But for instance, ARM processors would have a different model. So what you typically need to do then is to define something in Java to say, here we have a model that, if it's not the same as the processor model, at least can be implemented fairly cheaply with the primitives that the processor essentially provides. And that's essentially what has been done for Java and other languages as well. So we look at the Java memory model. That works by defining a happen before relationship. What happened before was essentially this thing to say we have these threads and they have actions, I1, A2, A3, B1, B2, B3. And then at some point happens before is essentially an arrow. So here that happens before would say, well, B3 happens after A1. So A1 happens before B3. So that means B3 gets to see everything A1 did. Every variable that got set by A1 is visible at this point. But B2 doesn't see it yet, even though maybe in actual time it was executed after A1. We don't guarantee that B2 sees the effect of A1. We don't guarantee that it doesn't see them either. We're sort of in the undeterminate zone here. It might see some of the effects of A1, or it might see none of them, or it might see all of them. We don't know, but we don't have a guarantee that it sees anything. Okay. So the first order that the memory defines is to say, well, within a same thread, we have a happens before. So these arrows are happens before arrows. A2 sees everything A1 did, and A3 sees everything A2 did, and so on. The second one is monitor locking. So we say unlocking a monitor happens before every subsequent locking of that monitor. So it means that if we have a thread and we have one monitor objects, and we have essentially here a synchronized zone and here a synchronized zone, then anything that happened in that synchronized zone or before is visible at this point. So every read, every write that was done by this block or that this thread did before it started the synchronized block will be seen at the point where the second thread grabs the same block. At that point, we have a synchronization. The third one is volatile fields, which I skipped for now. I'm going to explain what volatile fields are in next week. Thread start, so a call to start on a thread happens before all actions of the thread. And finally, thread join or termination, an action in the thread happens before another thread that completes a join on that thread. So that we have already seen. And then we say that's a partial order. So it's transitive. So if A happens before B and B happens before C, then A happens before C. Okay, and the rule then is, so now that we have defined this happens before, if any two operations are in a happens before relationship, then B is guaranteed to see all the memory effects of A. So that's the guarantee we get. So let's just look at one example, and we will come back to this next week because we are already over time. So here's the example. So we have these two threads. They both do a synchronized. Can the second thread print 0? So the second thread says, if the variable is set, then print A. What do you think? The answer is no, you cannot see 0. We have a guarantee. The guarantee is because what must have happened for the second thread is, let's see. Yeah, so the question is, so if we have this situation, so that's the first thread, that's the second thread, then we have here the synchronized block where we set equals true. And here we have the synchronized block where we ask if set. And because we have the same synchronized, there is a happens before, and it goes like this. And because we have program order, we have essentially A equals 1 was done here in that same, sorry, before the synchronized, yeah. So A equals 1 was done here, A equals 1. Initially, A was 0. Okay. So because we have a program order, it means A equals 1 happens before the synchronized block here. And that synchronized block happens before the next synchronized block. And because it happens before it's transitive, a equals 1 happens before the print. And that means the printer must print 1. It cannot print 0. Let's quickly go around and say, well, could the thread, could the thread have seen set equals true without that monitor, without that first monitor going in the synchronized? And the answer is no, it can't see that because initially set is false, so that happens now before, and it can't see any other memory effect. So it must be false, unless we have the situation where the first thread goes into a synchronized block and the second thread goes into a synchronized block. So that shows you essentially some of the guarantees that the model provides. And we will revisit that next week in more detail. We will also look next week at ways to write essentially even more efficient concurrent programs that don't need synchronized monitors. So that will be our program for next week, but since it's already past 4, we'll stop here. Is there any questions? I'm staying around for a little while. Thank you.
Thank you.
Bye.